Good morning, everybody. Welcome. It is Thursday, September 14th, 2023. This is the third lecture of this wonderful opportunity of this mini course that I've been invited to deliver during the focus period in network dynamics and control at the University of Linkoping, as it's stated here. Yesterday, near the end of the lecture, I defined what it is meant for a function to be strongly convex. So this is a function, just to be clear, it's always good to remember domain and codomain, right? It's a function from Rn to R, a scalar valued function, and it's strongly convex when everywhere in space, or maybe it's locally strongly convex, but in any case, right now, let me just do the theory for global. Everywhere in space, you take a point, and you can lower bound the function not only by a line in two dimensions or a plane or a hyperplane in higher dimensions, but actually you can even make the lower bound positively curved, right? And this coefficient is called a strong convexity parameter, and we saw that the strong convexity parameter ends up being the strong contractivity rate for the continuous time gradient descent. So that's a very simple example, and this particular example relies upon the two norm, unweighted two norm. And the proof, there are two ways to doing the proof. One, the simplest one is to look at the Hessian. That requires assuming twice differentiability, and the more interesting proof that could be an exercise, and you can find it on the web, is the proof of the fact that property number these two properties are equivalent. The first property really just stating the lower bound, and the third property here, it's all the numbers here. I got the wrong numbers just like yesterday. I need to fix. Let's call this 2 and 3 like yesterday we did. So the fact that 2 and 3 are equivalent. Now, then yesterday, I think I started to talk to you about gradient dynamics in the context of constraint optimization, and considering first to begin with the linear equality constraint, which is actually a little bit easier than the linear inequality constraint, which is very important case as well. And maybe we can discuss that offline if any of you is interested. This dynamical system here, x star equal to minus the gradient of f, minus a transpose lambda, and then lambda dot being equal to ax minus b. These are, as I mentioned, the classic Hurwitz arrow dynamics. Nowadays, people just call them Primal-dual gradient dynamics. And they seem to work, and the question is how well do they work? And essentially, you would like to come up with simple estimates for the contraction rate and understand what is the norm with respect to which this dynamics is contracting. And in this slide, there is one statement, but there could be better statements if I was more careful in doing the calculations. I will show you the calculations later. And what you would like to do is you would like to parameterize the entire problem by just a few insightful quantities. And in this case, there are 4. And these natural quantities are the strong convexity parameter, which is the lower bound on the Hessian. And this is called the strong smoothness parameter, which is the upper bound on the Hessian. And then the problem, of course, is also defined. So that describes f fully as a strongly convex and strongly smooth function. And then the problem is also defined by the matrix A and the vector B. Lowercase b plays no role essentially in what follows. But the matrix A is at first assumed to be to have independent rows, so that A transpose is a full rank positive definite matrix, and A min, A max are upper and lower bound. Essentially, they are upper and lower bound on the singular values of A. But if you look at the formula and think about it carefully, on the square of the singular values. But it's okay. You can, if you want, you can define them without the square. It doesn't matter. Now, what I told you yesterday is that it is possible to define a certain P matrix. It is possible to compute the Jacobian of F, primal dual gradient, and this is going to look like a matrix of the form minus Q minus A transpose, A and 0. I'll give you a second. I think you can see that that's the case. When you compute the Jacobian, you take all of the partial derivatives, where the matrix Q, well, the matrix Q is essentially the Hessian of F, and therefore the matrix Q lives in the same. Maybe I shouldn't even introduce an extra symbol, but I didn't want to go around with the Hessian of F in the proof, so I abbreviated that by introducing a single positive definite matrix Q. So the thing is this, that you can either think of this as a Jacobian, which is therefore going to be state dependent. This is it just happens to be only a function of X because lambda goes away. And then it's Q is a function of X because the Hessian is a function of X. You can either think of this as a state-dependent matrix, the Jacobian, or you can imagine that you are working with a collection of matrices Q that lives in a set described by these linear matrix inequalities. And you wish to ensure that the contractivity LMI holds everywhere in that set. So let me just remind you that, right, if I have the contractivity LMI for so what do we have? We've just decided that this is our matrix copy. We put it here to make a little bit of extra space. There is no minus sign. So I know this is our state matrix. Maybe I can abbreviate it with script A. I need to find the matrix P, which has to be symmetric and positive definite, and a bound L such that, actually, why don't we go directly with contractivity and a contraction rate C positive, such that you satisfy the contractivity LMI, which is A transpose P plus PA less than equal to minus 2CP. Does that make sense? So as we were discussing yesterday, when the right-hand side is 0 and you ask for strict negative definiteness, so if I were to have written A transpose P plus PA strictly less than 0, that would be the stability LMI. And I would call this the contractivity LMI with rate C. And they're, in some sense, they're equivalent in the sense that if you satisfy this equation, then there exists a C such that if you have a second equation, there exists a C that makes the first equation come true. And if you satisfy the first equation, then for sure you satisfy also the second. Does that make sense? Any questions? Is it?
It seems that you have an equation with the Banach moments.
Yes.
And P doesn't, it must be the same for all.
That's right. Yes. No, we're not going to do that. That's a very good point. We are going to say that Q takes value in a set, and the set is mu min identity less than equal than Q, less than equal than mu max identity. And what happens is that we are going to, ask for, first of all, we were saying that these two equations were equivalent, and that's done, nice and done. What happens is that we are going to ask for these together to hold. So basically, I will want to find a P matrix, positive definite, so that this LMI is always satisfied, even if Q is not unique, but rather Q is an arbitrary matrix ranging in that set, taking value in that set. Does that make sense?
And from the computational point of view, you need only to check the extremes, because here you have to, in principle, to check an infinite number.
You have exactly. We'll just do it all with LMIs later on. Yeah, but I don't know that you can just check the extremes. No. Yeah. So before I go into this proof, which will come with its own challenges, let me show you an application of this result about Primal-dual. So again, we are minimizing f of x subject to ax equal to b. So I'm going to talk to you about something called distributed optimization. In order to do that, let me talk to you about graph theory for just a few seconds. I hope you know it. If you don't know it, it's okay. This will not affect what follows, and I can introduce you to these concepts later on. So I would like to consider an undirected, weighted, and connected graph over n nodes and m edges, and I let capital L denote the Laplacian of this graph. Lambda 2 is algebraic connectivity, which is the smallest non-zero eigenvalue of the Laplacian, strictly positive, because the graph is assumed to be connected. And then I am also going to define another quantity, which is less famous, and that is the ratio between lambda 2 and lambda n. Lambda 2 just being defined as algebraic connectivity. Lambda n is the largest of the eigenvalues of the Laplacian. So this number is 1 or less than 1, because lambda n is the largest. Additionally, there's something called that one can define called the oriented incidence matrix B, which is a rectangular matrix with a number of rows equal to the number of nodes and number of columns equal to the edges. And each row of B describes the various edges of the graph. Imagine that your optimization problem is decomposable. And what I mean by that is that the cost function f happens to be the sum of functions f sub I, and I wish to think of an I runs from 1 through n. So these are the nodes of the graph. At each node of the graph, there is a cost function fi. You can think that fi is private to the node I. It's as if I have my own cost function. You have your own cost functions, and I don't know your cost function. And now imagine that each node I am going to imagine that x takes value in the reals for simplicity. So it's a function of a single scalar variable. And then I will imagine that each node has an estimate, xi, of the global variable. So at each node, I have my own estimate of what the final optimal x will be, xi. Moreover, each node, no moreover. Therefore, the full state of the network is a vector that contains all of the estimates that each node has. So therefore, here I wrote subscript because I don't want you to think that x is a vector in an n. X is a scalar. The variable that we're trying to compute is just a scalar. But now I have n computers that are trying to compute this x. Each computer has its own local estimates, x sub square parenthesis I. My estimate is x square parenthesis 1. Simone's estimate is x square parenthesis 2. And collectively, the system has a variable, which now is a vector with n entry, as many as the number of nodes. Now, when we want to solve the optimization problem in a distributed way, what happens is that we would like to ensure consensus among the variables, the various states. So I want to make sure that at the end, after I have converged, my estimate is equal to the estimate of every other node. So therefore, we have all computed the same X star that solves the optimization problem. Question?
All right, so is fx just the scalar function of the
Yeah, that's right. In this particular case, for simplicity, we're doing the scalar case. Otherwise, you need to introduce something called Kronecker products, which are useful and helpful, but the notation gets more complicated. So in graph theory, it is well known that there are two ways to impose the constraints that x sub 1 is equal to x sub 2 is equal to x sub n. There are two ways using two matrices. They're equivalent ways. These are two different matrices that you study in graph theory. As I just defined, L is the Laplacian and B is the oriented incidence matrix. The Laplacian is unique and the oriented incidence matrix is unique after you assign an orientation to the edges of the graph, which is arbitrary, but it doesn't matter at the end of the day. So do you see that I have now obtained a linearly constrained, strongly convex optimization problem? Why is that the case? Because I am going to assume that fx is strongly convex. In fact, I can consider each fi strongly convex, and I am subject to any one of these two equality constraints. So I've obtained a problem of the form that I had before, of like this, right? I'm minimizing a cost function subject to equality constraints, which are the consensus constraints. So at each node, I want the final estimates to all agree upon a common value. Now, let's start perhaps by looking at this equation here. So we are optimizing the sum of the functions fi's. At each fi, I evaluate the function of the estimate I. This is for node I, and I am minimizing it with respect to my own variable, subject to the equality constraint. So the equality constraint, when written with the incidence matrix, leads to this equality, xi minus xj equal to 0. And so after, ultimately, everything I said so far is subsumed by the fact that I can write now the Primal-dual gradient for the optimization problem that I just outlined here, for this optimization problem. And I can write it, for each variable. And after you do that, you will notice that the dynamical system that you obtain is distributed in the following sense. If you are at node I, you perform the gradient of your own private cost function with respect to your own variable xi. So you have this information and you can execute it. And then, if you are node I, there are a collection of edges. Let's call an arbitrary edge E, connecting nodes I and J. And along each of these edges, you can introduce this Lagrange multiplier lambda, just like we did for the Primal-dual problem earlier. And this would be the piece. Remember, we had minus A transpose lambda. The A matrix is equal to this transpose of the oriented incidence matrix. And when you write it in components, you get this formula here with the two terms. It's a bit tedious. It's just bookkeeping. It is not, rocket science. You just have to sit down, remember the definition of an incidence matrix, and plug everything together. And we could do that, but it would take 20 minutes, and I prefer using it in more efficient ways. And then you need to write the ODE, which was lambda dot equal to AX minus B. That was the general case, right? The ODE for the Lagrange multipliers in this case ends up being super simple, and that being that the Lagrange multiplier lambda associated to the edge E obeys a very simple OD, lambda E dot equal to Xi minus Xj. What have we learned? We had proved that what we have learned is that this dynamical system here, let's call it star. Now let's call it let's call it star B there, because we're using the B matrix. So that dynamical system is just an example of the Primal-dual gradient flow of 3 slides back. It's just I've plugged in as constraint matrix A, I have used the incidence matrix, I have assumed that the cost function f was the sum of cost functions, and I've obtained a distributed optimization algorithm. But then the result that I had stated earlier for a general Primal-dual gradient immediately implies that this incidence-based distributed gradient flow is strongly infinitesimally contracting with respect to an appropriate weighted 2 norm that I'm not going to write down right now. It's the one that we discussed. But the good news is that I can write down the rate for it. I can write the contractivity rate. Now, there are some details that I'm just going to skip right now, and I'm just going to tell you this is the answer you get as you do the calculation. And you make also an additional assumption that I'm going to skip. So if you're interested in this, we can sit down and work out all the details. Or the details are in this paper that we have, which is on the archive right now. You can just download it even just later today. So now, at the end of the day, after some calculations, you get a contraction rate for this incidence-based distributed algorithm. And this rate is, well, okay, let me remind you, the formulas are, it's coming from here, right? We had this estimate, we had the 1/4, we had the minimum. It turns out that I am going to neglect this first term for a reason that I don't want to explain right now. And then this mu minimum is the contractivity rate of, it's the smallest eigenvalue of Q. And then I have A min over A max. All right, so what is A min over A max in the case of the incidence-based optimization? So A min over A max, you need to multiply the constraint matrix A, which is equal to B transpose, with itself transpose. So then I obtain B transpose B. Now you go back to your favorite book on algebraic graph theory and network system. In this case, I'm using my own, but these are known things. It's not novel. B transpose B is equal to the Laplacian matrix for the graph. And actually, right. Let me, I made a mistake. It's not equal to the Laplacian matrix. It's equal to the edge, something called the edge Laplacian of the graph. And what happens is that the edge Laplacian of the graph is a matrix that has exactly the same eigenvalues as the Laplacian, except that when the graph is a tree, it does not have any eigenvalue equal to 0. So a little bit of a story here about graph theory. The bottom line is that you have this bound here with LMI, which tells us that the edge Laplacian is lower bounded by lambda 2 and upper bounded by lambda n. 2 slides ago, those were the coefficients A min and A max. Do you remember that, right? Because 2 slides ago, we had A transpose, right? Any questions at this point in time? Yes.
So you have 2 different ways to enforce this consensus. You get different contraction rates.
You are 1 step ahead of me. The answer to that question is precisely in the next 2 slides. Yeah, I was precisely getting, the whole point of this entire detour is to get to the 2 rates. Yeah. All right. So, but I hope it is clear that I need to compute the ratio between A min and A max. That was in the formula for the contraction rate 2 slides ago. And here, doing a little bit of graph theory magic, but it is just linear algebra. I get that the two coefficients A mean and A max are lambda 2 and lambda n, the eigenvalues of the Laplacian. So that the rate here, this should have been A mean over A max, right? And I write lambda 2 over lambda n because I did the calculations and my constraint matrix satisfies that equality. This is still the Sami.
Okay. I'm a bit confused about the hypothesis of the tree.
Because
you know, here you have a lot of degrees of freedom that you are not explaining to us, because somehow you can have constants in front of the. Also, the Laplacian might be a Laplacian of the weighted graph. And for instance, why this tree condition is needed? If you don't have a tree, it means that you have extra constraints that are. Probably you are against one of the hypotheses.
No. So, in fact, both of the last two questions are perfect because they're exactly the two things I wanted to say. So why am I assuming a tree? Well, because this standard treatment here of the Primal-dual problem begins with a simplifying assumption that I do not have redundant constraints. And so I assume that the rows are independent. And then when I compute a transpose here, I obtain a matrix which is strictly positive definite, so that A mean is strictly positive. Does that make sense? So in my first slide on distributed optimization, when you look at the graph which has n nodes, and you assume it's undirected, and if you take it to be a tree, which is a connected, undirected graph through all the nodes, then these are my 1, 2, 3, 4 nodes, and I have 3 edges. And now it is known that B is full rank, And when you do B transpose B, you get that it is positive definite, lower bounded by lambda 2. And if you think about it, what's happening here is that along this edge, you're writing, if these nodes are 1, 2, 3, and 4, you're writing x1 minus x2 equal to 0, x2 minus x3 equal to 0, x3 minus x4 equal to 0. Those constraints are not redundant. However, imagine now that I have a graph which is not a tree, it has a cycle. You are now imposing an additional constraint. You're imposing x1 minus x3 equal to 0. That is a redundant constraint. Does that make sense? So the second question I received is, how do you essentially, let me transcribe it. How do you handle the case where you have redundant constraints? If you have redundant constraints, it should still work, but I absolutely need to generalize this assumption here. I need to be able to handle the case where the constraints in A are redundant. In fact, it's very important that I handle redundant constraints because, and allow me to introduce briefly the Laplacian problem. In the Laplacian problem, very much everything happens in the same way. I can set up the cost function, I'm going to decompose it, and I set up the constraint that tells you that all of the estimates at each node need to achieve consensus, so that we all have. And then I can write down the Primal-dual flow, which I'm going to remind you, it's x star equal to minus gradient of fx minus A transpose lambda dot equal to ax minus b, right? But now my ax equal to b is the equation Lx equal to 0. They're linear equations, right? So it's really just the Primal-dual, just that I plugged in the graph objects that define the linear constraints, the consensus constraint, and I obtain my specific expression for the Laplacian-based distributed gradient 1, 2. So this is called Laplacian-based distributed gradient, in the last slide, it was called the incidence-based distributed gradient. So they're both examples of Primal-dual, just really no more, no less, with some particular structure. Now, the constraints that I have used is Lx equal to 0, and everybody, so now L is always known to be a square matrix of dimension n, an end of rank equal to n minus 1 under the assumption that I have an undirected graph which is connected. And specifically, it's always known that L1n is equal to 0. So we also have an explicit expression for the kernel of L. So L embodies a redundant constraint. So both, in the Laplacian case, I cannot possibly avoid it. There are redundant constraints. In the incidence-based problem, I have redundant constraint every time my graph is not a tree. If it has cycles, each cycle gives you redundant constraint. Now, it turns out that, and now comes the answer to Sandro's question. It turns out that if you have a positive if you have a positive semi-definite matrix, any positive semi-definite matrix will have some eigenvalue equal to 0 and some eigenvalues that are strictly positive. Does that make sense? Now, you can always write an equation of this form where pi n is the orthogonal projection onto the subspace of the eigenvectors which corresponds to strictly positive eigenvalues. All right, so you have a symmetric matrix. The eigenvectors are all real. Some eigenvectors belong to the kernel of the matrix, which is they correspond to 0 eigenvalues. Either eigenvectors are the one associated with the strictly positive eigenvalues. The eigenspace, the vector subspace generated by the non-zero eigenvectors, well, the eigenvector corresponding to non-zero eigenvalues, that is a perfectly well-defined vector subspace, and you can define the orthogonal projection onto it. In the case of consensus, it is well known that this orthogonal projection matrix admits a very famous expression. Sometimes this matrix has all sorts of names. It's used in signal processing. It's called the centering matrix. Anyway, this matrix, if you multiply it on the right by a vector, let's call it V, what this matrix does is it takes V, and by means of this particular operation, it removes from V the average of V. From every entry of V, the average gets removed. Anyway, this is an orthogonal projection. By the way, orthogonal projection matrices are symmetric and positive semi-definite because the eigenvalues are 0 and 1. And so here I have written a LMI upper and lower bound for my matrix L. It's upper bounded by the largest non-zero eigenvalue, lambda n. It's lower bounded by the largest non-zero eigenvalue, lambda 2, which is, but then I had identity earlier, right, didn't I? Now I cannot put the identity because this matrix is positive semi-definite. It has an eigenvalue equal to 0. It cannot be lower bounded by a strictly positive definite matrix. It can only be lower bounded by its own projection matrix describing the non-zero eigenvalues. Does this make sense? Okay, so now we really got into the thick of things with a lot of linear algebra and graph theory. What am I going to tell you? I have put a dagger here. This dagger is to answer the question that I have received. What happens when there are redundant constraints? When there are redundant constraints, everything still works with an asterisk or a dagger. And the asterisk is that your dynamical system is defined on, so let's say here, in this particular example here, in the end, I have, well, earlier I had n plus m, right? here I have n variables because there are n nodes, and then I have n Lagrange multipliers. So I am living, it appears as though I am living in R2n. I have 2n variables. However, you can show that this particular primal-dual problem lives on a vector subspace of R2n. Given the initial conditions on the Lagrange multipliers, you do not leave a 2n minus 1 dimensional subspace. And it is in that subspace that your dynamics is strongly contracting with a given rate, which we will discuss in a second. Am I making sense? So redundant constraints appear to give you a problem, but if you think carefully about the primal-dual gradient flow, you will soon realize that it is not evolving in the full space of primal and dual variable, the x and lambda. You don't live in Rn plus m. You live in a vector subspace, which is forward invariant. And then, with a little bit of work, you can show still that you have contractivity on the subspace. And some people would call that semi-contractivity because you're not contracting on the full space. You're constructing, pardon me, you're contractive on the vector subspace. Does that detour make sense? There's a question.
So if there are redundant constraints, can't you just throw away?
Yes, you certainly can. You certainly can. It's especially easy to do so when you have the incidence-based constraints, because you come in here and instead of implementing Lagrange multipliers for all of the constraints, you just select a tree, a spanning tree of constraints, and you implement those. It's a little less clear how to do it here because now the constraints are all appearing inside the Laplacian matrix. I don't know that I have a clear idea of which lambda or how to drop, how to change this dynamics.
Drop one.
You drop one, that might be enough. It might be enough.
You can do projection in the first equation.
I haven't thought about it, so when I haven't worried about it too much. I've simply proved that redundant constraints, you live in a vector subspace, and there's a theory which is in the slides. I may have time to talk about it. If you're interested, it's in the slide later on. And it talks about semi-contractivity when your dynamical systems lives in a vector subspace. Just to be clear, things are not too complicated because a vector subspace is still a subspace. You have a vector you have a subspace, you have a vector space, you define a norm on it, and then the theory should work, right? All right, so let me just show you a picture. But to show you the picture, I wanted to go back to the question that I received. If you do all of the calculations based upon this theory, you obtain that
What are nu I?
nu I are the strong convexity parameters of the private cost functions. So remember that what I need to do is I need to decompose my total cost function as the sum of private cost functions. And this is a scalar case. So I need to assume it's standard, to the best of my knowledge, in this literature, it's relatively standard to use strongly convex functions at each node. And then the sum of strongly convex functions, it's going to be strongly convex as well. And now you have n scalar strongly convex functions, and you put them together, you do the sum of them, and you ask, what's the strong convexity parameter of this function? It is the smallest of the stronger convexity parameter of each of the private functions. Does that make sense? You can see that. It's a little exercise. All right. So, right, this is the function that has to be strongly convex in the n copies of R, right? So I have each of the estimates at each state, and I have a sum of strongly convex function of each entry. If you compute the Hessian, it's going to be diagonal, and you're going to pick out the smallest eigenvalue of the Hessian, which is the smallest of the strong convexity parameters. And that minimum of mu I appears in both cases, appears whether you're doing the incidence constraints or whether you're doing the Laplacian constraints. In both cases, you get the 1/4 factor because that comes from the estimates in the Primal-dual. And then in the first case, when you're doing the graph, the incidence matrix, you've got this lambda 2 over lambda n, which is for B transpose P. And that's the edge Laplacian, blah, blah, blah. In the other case, if you look at this equation, there's something that I don't want to mislead you. This is a bound for L. L is plays the role of the constraint matrix, but I need to do L squared. I need to do L times L transpose. L is symmetric. So I really need to use as A min and A max, not the singular values of L, the square of the singular values of L. So I'm going to need to use lambda 2 and lambda n squared because I have because in the bound I had A transpose, right? And so here what happens is that for the Laplacian-based constraints, my best estimate, doing the bookkeeping correctly and honestly without cheating, I obtain lambda 2 over lambda n squared. Lambda 2 over lambda n is clearly less than 1 because you're taking the smallest eigenvalue and dividing it by the largest eigenvalue. It's always less than 1. So what have we learned? If you're not careful, you will think that what you have learned is that the Laplacian-based constraint algorithm is slower because it has a smaller contraction rate than the incidence-based constraint. The two formulas seems to say that. What is wrong in my thinking? That's exactly right. I have only shown that in my limited ability of calculating the contraction rate, my estimate of the contraction rate is I get a faster estimate for incidence than I get for Laplacian. But that does not mean that the true eigenvalues and the true convergence rates are like this. They could be very different, right? So here's what Anand very recently has performed. So first of all, before we continue, lambda 2 over lambda n, it's a very cool quantity. It's a very interesting quantity that naturally appears in the literature. People have studied it, just like the algebraic connectivity lambda. Okay, lambda 2 is so famous that I don't even like, it's a super famous one. Everybody knows that there is the algebraic connectivity. But in the context of oscillator networks, there is an analysis method called the master stability function approach, which is widely studied by physicists, dynamical systems people, and so forth, and network scientists. In the MSF, master stability function approach, the ratio lambda 2 over lambda n is known to play an important role in the synchronization of coupled oscillators. I'm not going to say more. That's why people call that the synchronizability parameter for the graph. Any questions? So we've seen that my estimate of contraction rate for the incidence had the synchronizability, and for the Laplacian is the synchronizability squared. The synchronizability is less than 1. So what you can do is very, very simple. Empirically, what you can do, you can just ask yourself the question, is it true that for a simple problem that one is faster? Which one of the two is faster? Is my prediction correct or is it off? And to make it even simpler, what you do is instead of having an arbitrary strongly convex function, which could be nonlinear, you take a quadratic strongly convex function so that its gradient is linear. If the gradient is linear, allow me to go back for a split second. If your gradient is linear, well then, but Francesco, is the gradient is linear, everything is simple, because if I select f to be quadratic, the gradient is linear. Now this is a linear system, and the linear system is going to have a matrix that describes it, and this matrix is going to be, oh my goodness, it's the one that we've been playing with all along. If I randomly generate graphs and I randomly generate the entries of Q, then I can just compute the eigenvalues of the matrix. I compute the eigenvalues of this matrix, and I look at the eigenvalue, I look at the spectral abscissa of that matrix, which is going to be the contraction rate for this linear system. Does that make sense? So in practice, I can eliminate the nonlinearity. Now I'm looking just at the matrix, and I just compute the eigenvalues without doing any fancy nonlinear analysis. And so here, Anand did the following: generated private quadratic cost functions where the contractivity rate, which he should really have used mu I, forgive me. That's okay. It's qi here, and then there's an offset vi, and we are uniformly sampling them between 0 and 10. And then we look at the graphs with 40 nodes, and for each value. And then we consider a random graph model. Have you guys heard of this thing called the Erdo-Shreni model? Okay, so I will assume you've heard of it. Otherwise, we can talk about it offline. So I select a certain probability of having edges. I generate the graph. If the graph is not connected, I generate another graph. So basically, this is the Erdo-Shreni model conditioned upon connectivity. And for each probability, I compute 50 graphs, and then I plot the mean and the standard variation of the spectral abscissa of the primal-dual matrix that you would get. Any question? So you simplify the nonlinearity, you look at random graphs, it's a stochastic result, just do a bunch of simulations, and then you plot them. And what do you plot? Dominant eigenvalue, or the spectral abscissa, of, in blue, it's the incidence matrix, well, the incidence-based primal-dual matrix, and in orange is the Laplacian-based primal-dual matrix. Does that make sense? And the dominant eigenvalue, well, the dominant eigenvalue is negative, but the contraction rate is minus the dominant eigenvalue, right? So they are negative. The good news is these quantities are negative, which is what you want, because you are hoping that the system is Hurwitz and the matrix is Hurwitz and you converge, right? But what's interesting is that, first of all, they are relatively close to each other, which means that perhaps it does not really make a big difference whether you run one or the other. And in fact, if at all, it looks like the eigenvalue that is larger in magnitude, which would be the larger contraction rate, is the orange case, which corresponds to the Laplacian. So in fact, these numerical results are precisely opposite to the predictions based upon the estimates that we have. And so what that means is that in this particular illustration, it means that the proofs that I will show you after the break, it will be a proof showing, I need to show you that this linear matrix inequality holds true. So we take the primal-dual matrix, where Q lives in a set, it's not a unique matrix. And I need to design a P matrix, which I have a formula for. I already have an ansatz. I have a conjecture for what P to use. And I need to show that this MI holds, where C is exactly this expression. And yet, I already know now empirically that, unfortunately, this is conservative, and I should be able to satisfy an even smarter LMI with a more precise expression of C. But that is future work for you guys to help me with. Let's take a 5-minute break, and then we'll continue. Welcome back. It was great to have a break and to prepare. So, as you remember, we've given the basic definitions of contractivity, and we're looking at examples. And we looked at this primal-dual example, which is very interesting because it leads to, for example, distributed optimization. I did not show it to you, but also the linear inequality constraint is very interesting and valuable. There is all sorts of, for example, classically studied problem of internet congestion control and resource allocation over a network is for the linear inequality constraint. And I'm not going to show it to you, but one can write ODEs with the flow that is strongly contracting and that will solve the linear inequality constraint. So now I have 45 minutes. I would like to try to do the following thing. I would like to show you some highlights of how do you prove this LMI bound. So we will do a little bit of LMI, and it is rather complicated, but you get to see what is the complexity in trying to get to this type of bounds and then trying to improve them. Because we just saw that we would like to improve the potential. And then I would like to show you other examples and maybe just quickly mention what they are. They're in the slides, you can read them later. And maybe take the time to work out an infinity norm contractivity rate. And we will do that for the case of a neural network. So that's my plan for this 45 minutes. Let's see if I manage not to spend too much time with the proof of the LMI. So let's do 10, 15 minutes of that. And if when I have exhausted you with it, we switch to something different, which is easier. All right. So here's the task at hand. We have a matrix that has this particular shape, minus Q, A transpose, A0. Two things. I'm going to call it, give it a name. Let's give it a name because, as I told you yesterday, it's always easy to have a name to call things. It's called a saddle matrix. Some people call it saddle point matrix. And also be careful because people call saddle matrices other matrices that have slight variations upon this theme. And also, I am introducing a parameter tau. So in what follows, imagine that tau is equal to 1. Therefore, I apologize if like a nuisance, but really it's just tau equal to 1. Tau is the time scale for the dual dynamics. I can make the time, if I make tau small, I can make the dual dynamics run faster. Now, I'm going to skip some details. In fact, we're going to do it for the case where the constraints are redundant, and I have a lower bound on A transpose, which is not the identity, but it is pi. Pi sub A, which is the orthogonal projection onto the perpendicular to the kernel of A, to the unit of A. A. Yeah. Or orthogonal projection onto the unit. And in fact, we can even do it for the case where Q is not symmetric. We're going to make it even more complicated. It's not symmetric, but I can define the minimum and maximum Q min, Q max anyway by just looking at the smallest eigenvalue of Q plus Q transpose over 2. This is minus log norm with respect to 2 norm of minus Q. But anyway, and I can also look at something related to the singular values of Q, which is Q max. And the details are not so important right now. The task at hand is, I wish to prove a contractivity LMI for a saddle matrix with respect to a P matrix, which is of this form. And because the P matrix is positive semi-definite, because I already know that there's redundancy, so I cannot have contractivity on the full space. P is semi-definite. I'm going to call this a semi-contractivity LMI rather than the contractivity LMI. So don't be scared. It's just that. And I have explicit expression for alpha and C, which are the two parameters that appear. Alpha appears in P, and C appears directly in the LMI. So how do I show that this thing holds? So first off, I need to show, I'll do it in 3 steps. The easy step is, well, let us make sure that I'm not making a mistake and my P matrix is in fact positive semi-definite, because there's no guarantee that if I put the A matrix there and I multiply by alpha, if alpha is too large, that matrix is not positive semi-definite. So there's going to have to be a bound on alpha to ensure that's the case. Is it true that for my alpha selected according to that formula, is it true that I don't lose positive definites? When alpha is 0, the matrix is clearly positive semi-definite because you have identity, and then on the second block is positive orthogonal projection matrix, which is positive semi-definite because it's an orthogonal projection, which means it's symmetric, and the eigenvalues of an orthogonal projections are 0s and 1s. So we're fine. Okay, so how do we do that? So I'm going to use a tool which is called the Shur complement. I have written it up there for you. Question.
Before we start, I'm going to go back to the previous slide. Why exactly this S and this P? How are you related to the problem?
Great question. S is the object that I would like to study. I would like to show that S, again, you can think of this as a matrix, but it's a parameter-dependent matrix. Q in S lives in a set. I would like to show that the matrix S satisfies an appropriately defined contractivity LMI. So why did I use this P? So S is given, you need to solve the problem for S. There's no degree of freedom there. In fact, ideally, I would like to do it for even more general saddle matrices. But at this point in time, I'm capable of handling this particular one. For example, I may want to put a symmetric positive definite matrix in the second block. I would like to do that, but if I do that, and then I don't know how to make the proof work for now. This is complicated enough. Why do I choose this P? I do not have a good answer to that. I choose this P because I can make the proof work with that P. It's a very bad answer. The real correct P could be very different. With this P, I get this contraction, I get this performance level, which is this contraction rate. If I was able to put a smarter P and do all of the calculations as in the next 3 slides, maybe I would get a larger contraction rate. That would be great. This is related to what we were discussing yesterday of the optimal design of the weights. If you give me a matrix A, a numerical matrix A collection of numbers, then I can run all sorts of LMI, all sorts of numerical calculations that will tell me the exact contractivity rate of that matrix. I can optimize P and get all the way to the spectral system of the matrix. I can do that for a numerical matrix. I can do that for a specific matrix. You give me a matrix, I can do it. But here I would like to do it for a set of matrices parameterized by these few parameters. I want A to be upper and lower bounded by A min and max, and I want Q to be upper and lower bounded by Q min and max in that particular way. And why am I interested in those sets of matrices? That's because originally I have a nonlinear system, and the Jacobian of the nonlinear system lives in a set of matrices. So if I prove contractivity for every saddle matrix like this, then I have proved contractivity of the nonlinear system. Does that make sense? Again, this is a beauty of contraction theory that I orthogonally decompose the problem. I have a nonlinear system. I compute the Jacobian. The Jacobian has some structure. This is the structure. And for that structure, now I'm going to do just linear algebra. Yeah, thank you for the question. Very helpful to clarify what's happening here. So I want to do, I want to use a tool called the Shur complement. So positive definite matrices, it's a world of its own. I mean, there are, we could have a course like this just on positive definite matrices, huh? But one little tool that is useful is the following. If I have a block matrix of this form, and I ask myself the question, is it true that this matrix is positive definite? Then the following is true, that this is equivalent to asking A being positive definite and C minus B transpose A inverse B being positive definite. And this matrix here is called the Shur complement. Any questions? Can you guys read in the back? Is it okay? Sorry. Now, oh, by the way, I'm not asking for my block matrix to be positive definite. I'm asking for positive semi-definite. And so I actually need to have an extension here. Actually, let me do it in a different color so that you can notice it. If I ask for this to be positive semi-definite, this is implied by this. So I will find one of the two blocks on the main diagonal is positive definite, and then I do the Shur complement, and I ask for it to be positive semi-definite. Questions? Now, if you go back to our P matrix, if memory serves me right, I put an identity here, I put alpha A transpose, and then I put a pi A there. Let me check before I make a mistake. Yeah, and let's just play with tau equal to 1. So if you see tau, just set it equal to 1, don't worry about it. And I did make a mistake. The transpose is here. Okay, so I do the Shur complement. If this is, by the way, this Shur complement here, I have done it with respect to the 1-1 block. So this is called the Shur complement with respect to the 1-1 block. But you could do it exactly with respect to the 2-2 block, and you would get equivalent. It just so happens to be the case that I am lucky. The 1-1 block is the one that is invertible. All right, perfect. And so then I need to write the 2-2 block, which is pi. So I want to show that P, which is my name, is positive semi-definite. I know that the 1-1 block is positive definite. So then I need to check with the Shur complement. So then I'm gonna ask for tau pi a minus alpha squared a squared to be positive definite because I calculated this thing. C is pi, then I get A inverse A is the identity matrix, so going away, right? And then I have B transpose B, but my B matrices are alpha A transpose. So I get two copies of A of alpha, and then I get A transpose. Any questions? Now, remember that, what do you remember? You remember that A transpose, we had calculated it to be lower bounded by A mean pi A. Sorry, let me make some space here. We had done that discussion earlier. So therefore, this particular LMI here is now equivalent to a scalar inequality. Because, okay, I have this parameter tau, we can set it to 1. 1 minus alpha squared, and this is lower bounded by A mean and, sorry, and upper bounded by A max. Right. All right, let me proceed. I have a question right now. I'll figure it out later. So now this inequality is now becomes a scalar inequality, alpha squared less than tau alpha max, A max. So I need to check that my alpha has to be sufficiently small. It cannot pass a certain threshold value. If alpha is too large, again, we discussed that when alpha is 0, this is 0, that's 0. Clearly, this matrix is positive semi-definite. So now, so the intuition already is that alpha cannot be too large. And the right value is the one that I just calculated, which is that alpha squared has to be less than 1 over A max. And now what happens is that you kind of wonder, how did we define alpha in the previous slide, which was, you know, very particular, but alpha was defined in this very particular way here. Let me collect it up here for a second, take the screenshot, copy, put it here, paste. This is what alpha was, right? And let's put it there, a little bit smaller. And so now there is a conceptually trivial, but tricky, you just have to follow through, derivation with standard, very simple inequalities that leads to show you that in fact it is true that if alpha is defined like this, then alpha squared is less than 1 over A max. And how does it work? Basically, you take the argument of this mean, it's the minimum of two numbers, and I square it. And the minimum of two numbers is always upper bounded by the minimum times the maximum of these two numbers. Does that make sense? Now, the product between the minimum of two number and the maximum of two number, you know what it is equal to? The product of the two numbers, because one of them is going to be the minimum and the other is going to be the maximum. And now the product of the two numbers is exactly what you wanted to show being the upper bound. All right. Okay, so we have performed the first step, which is check that your proposed conjecture, your ansatz, your proposed P matrix is positive semi-definite. Because if it's not, you've got a problem. Now we go into the heart of the problem. What is the heart of the problem? It is this particular LMI here. Okay, so S transpose P plus PS less than equal. Okay, so oh, here it is. So I don't need to copy it. It is here. This is what I need to do, right? Prove that. Actually, it was written slightly differently. So I need to prove that S transpose P plus PS is less than equal than minus 2CP. And then what I do is I take this and I bring it to the other side. And so then I end up so that I have something greater than or equal than the left-hand side, which will be 0. So the point is that I'd like to rewrite this LMI in such a way that I ask for something to be positive definite. All right, this is equivalent to when you're doing in high school, you're doing linear equations, you bring everything to one side, make sure it's greater than 0. All right, fine. So now you have the products of block matrices, right? So here's what happens. This left-hand side here, which is equal to that. Here I haven't done anything. I've just copied the matrices. This is S transpose P S. No, sorry. S transpose P P S, and then it's minus 2CP. Any questions? So you literally roll up your sleeves and you write it very carefully and you check it 5 times. Then you multiply everything together and you obtain this beloved, beautiful object here. So as a famous mathematician once said, this is an equation that only a mother can love. So that's the joke, or a father for that matter. And by the way, this is not my equation. This particular derivation originates in a paper by Kwanan Gu and Lina, so which is cited in the slide. So now, this looks very complicated. It is a 2x2 block matrix, and you want it to be positive definite. So you would like to apply the Shur complement, which is there in green. The same idea, so that you go from a 2n problem to an n problem. So you want to use the Shur complement again. But before doing that, I wish to ensure that one of the 2 blocks, the 1, 1 or the 2, 2 blocks, are strictly positive definite. Because if I want to apply the Shur complement, now it was in the previous slide, I need to do the Shur complement with respect to either 1, 1 or 2, 2, and I need that block to be positive definite. You know why I need it to be positive definite? Because I need to invert it. If I don't have one block that is strictly positive definite, I'm not quite sure exactly what I mean by the inverse of it. All right. So now in this slide, let us use the 2, 2 block. All right. What is the 2, 2 block happens to be? So the 2, 2 block is a bit complicated. Here it is. But what I am going to show is that it is strictly positive definite. And so how do you do that? Well, you've got, here's the matter. There is the alpha parameter and the C parameter, right? Both of them are present here. But they were related to each other because 2 slides ago, if you remember the definition of alpha and C, I also have this other piece of it here. C is 1/2 alpha A mean. All right. So C is related to alpha in that particular way. And so here, when you expand it out, you do the calculation. So here's what's happening. Look at this thing. You have something which is positive definite, which is good, minus something which is positive semi-definite. So this is a good term against a bad term. You needed the good term to be larger than the bad term, right? Because you want a positive definite. So the good term has a 2 in front of it. Okay. So you know what I'm going to do? I'm going to take half of the good term and I'll put it in a parenthesis with the bad term. And the other half, I keep it for later, for a later enjoyment. And then I'm going to show that this good term and that bad term, I want to show that this basically more or less goes away and I'm left with something positive. Okay. And so what happens is that 1/2 of the good term multiply the bad term. You do the simplification, you use the formula for C as a function of alpha, and this is exactly C as a function. So this term, this is exactly C. So it's C minus C. And so this goes away. So what I've shown is that half of the good term is exactly equal to the bad term. To be precise, I'm lower bounding A transpose by A mean times pi A. So there's some conservativeness here. But at the end of the day, I have shown that my 2, 2 term is lower bounded by something that is strictly positive definite. So I have 2 times alpha A transpose. One of the alpha A transpose takes care of the bad guy. And then I have alpha A transpose. Does that make sense? Now, here's another dirty, infamous trick. So let's come to this formula. Allow me to use a trick of my editor. We have shown now that I can essentially eliminate that term, right? And I eliminate the 2. Okay, perfect. Now, if you look at that equation for a few minutes, you will realize that this 2 by 2 matrix can be written as this product here at the bottom. What is this product? It is a congruence transformation, because I have on the left-hand side identity A, and on the right-hand side identity A transpose. So this matrix is the transpose of that. It's not the inverse, it's the transpose of it. So it's a congruence, not a similarity transformation. And the reason I do that is because when I look at it, I see the A matrix appear a lot of times in precisely just the right way. And then the advantage is that because congruous transformations do not change the inertia of the matrix, which is the pattern of zeros and positive eigenvalues, is not changed by a congruous transformation. Actually, I think I am exaggerating it here. I think what I'm trying to prove is that this is positive semi-definite. And if I prove that this is positive semi-definite, then I'm okay with that particular, because this congruous transformation could be rank deficient. And so I could be changing the inertia, but it doesn't matter. So in what follows, for the purpose of what follows, it will suffice to show that this matrix here is positive semi-definite. Because if this is positive semi-definite and I do a congruous transformation, the resulting cannot be, must be positive semi-definite. Perfect. Okay, so we have checked that the step 1, checking the P is positive definite. Step 2 was eliminating some terms essentially by some tricks. And now I have achieved a feat. The feat is that the 2-2 block is just the identity with an alpha. So I am ready to do the Shur complement with respect to the 2-2 entry. And on top of that, it's just identity. So when I have to do the inverse of the identity, it's just identity, right? So I don't have to worry. So the Shur complement is going to be the first term minus the 2-1 multiply the 1-2. And then there will be the inverse of this, which is just 1 over alpha. Does that make sense? So in the next slide, the third and final step will be, is it true that the 1-1 term minus the 2-1 times 3, 1-2 times 2-1 term, that Shur complement, is it positive semi-definite? And if I achieve that, then I am done, right? Okay, so here's what I say here. I say, because the 2-2 term is strictly positive definite, suffices to show that the Shur complement is positive semi-definite. So in equation 9, I write the Shur complement. Hopefully I did the bookkeeping correctly. I have checked it 10 times, not 5. And Anand and Sasha and others have checked it. So this proof method is the one by Lina and Kwanangu, but by now the formulas have changed. We've done this elimination of the congruous transformation is not in the proof, and then everything becomes a little different. So now you write the formula for the Shur complement. That's equation 9, and then what you do is you put on the left hand side here, you reorganize the terms in a way that will be helpful. I don't have a better explanation for it. Basically, this is the entire formula, and there's nothing wrong with that, of course. That's just a formula. And then I take all of those terms, and it's just convenient for me to put some terms on the right-hand side, and then the sum of 2 terms on the left-hand side. In fact, even better, I apologize. Both the left-hand side and the right-hand side are the sum of 2 terms. So I have 2 terms on the left-hand side are greater than or equal than 2 terms on the right-hand side. And the reason I organize it this way is because the proof works. Because I know where I'm trying to go. So this is called, my friend Bassam, Professor Bamier says, LMI acrobatics. Right now, have you ever seen these people swing? Like you're holding on and you swing, and then at the end you have to grab. So it either works And if it doesn't, you are nowhere. I mean, you haven't gotten anything. So the reason I have reorganized the left and right hand side into the sum of two terms is because now clearly you will agree that if I take if the first term is greater than the first term on the left hand side is greater than or equal to the first term on the right hand side, and the second term in the right hand side is greater than or equal to the second term in the right hand side, then that's a sufficient condition for the inequality to hold, right? And so exactly that's what I wrote here. I wrote the first term on the left hand side is greater than or equal than the first term on the right hand side, and then the second term in the left hand side is greater than or equal to the second term in the right hand side. Why did I do this? The proof lies in the pudding, as they say, because I can do the next steps. Let me finish here. I don't want to do the remaining details. They're not important. It just so happens to be the case that these terms are very nicely designed so that now all of the calculations with all of the coefficients work out. In fact, the way I define Qmax is just so that this equation works. And then here I'm going to use Q mean, and you play. That's why alpha and C have those weird looking expressions. Okay? I don't think there's much more to be learned from this proof right now. But the lesson is the Shur complement is very useful. Positive definite block matrices are very useful because they just appear in nature like Primal-dual gradient. They're called saddle matrices. They're widely studied. Setting up these LMIs, it's a tricky business. And you already know the estimate for C is conservative. It even leads you to the wrong graph theoretical predictions. But that's the best that we know how to do at this moment in time. That these are the best rates available in the literature. All right. At this point in time, let us make this more lively. We have completed the discussion of the third example. So, and I think I've written 10 or 12, so there's quite a bit of work to do. So the next thing I would like to do is, without doing any proof, and also without even going into too many details, I would like to talk to you about generalized gradients, which are called proximal gradients. And inside the proximal gradient is a generalization of something called the projected gradient. So the proximal operator is defined in here. If you give me a function g from Rn, a scalar function g from Rn to R, then you can define the proximal operator of it. And think of it as a smoothed version of a projection onto a proper set. So right now, all of the definitions are fine. So let me give you just one example of what this definition does. Suppose that you have a convex compact set here, C. And suppose that your G function is the orthogonal projection. No, I apologize. Your G function is kind of like an indicator function. It gives you 0 or plus infinity. G of x is equal to 0 if x belongs to C, infinity if x does not belong to C. Okay? So it's an indicator function of sorts. And I'm going to want to solve an optimization problem. My optimization problem I want to solve is I want to minimize f of x subject to x living in C. Okay? This optimization problem is the same as minimizing f of x plus g of x with respect to x. Do you see that it is the same problem? Because my function g goes to infinity as soon as I leave the set. So it cannot possibly be true that the minimum is outside of C, right? Does that make sense? So this is called, in optimization theory, is called a composite optimization problem. And this problem, why is it composite? Because I have a cost function, which is the sum of two terms, f and g. F is very well behaved. F is your friend. F is where you put everything that you know. It's a strongly convex function. And G can be a complicated object. For example, it maps not to R, like I said at the beginning, but to be precise, this is not a function into R. It's a function into the extended R, because it goes to infinity as well, right? So this function, I'm not going to tell you all of the properties that this function must have in order for the theory to work. Just says that I need a function to be convex, closed, and proper. And people use the abbreviation CCP. It's a beautiful, beautiful theory, very widely, very modern optimization theory. So, for example, in modern textbooks on gradient algorithm, you will find the proximal operator for sure. Chapter, it's not going to be chapter 1 or 2, it's going to be chapter 4 or 5. Now, you have this projection, you have this function G, right, that maps to 0 or infinity. But what you would really like to define is the projection onto C. It just feels to me like the projection onto C should be an interesting operator. This is an operator that if you give me a point X, it projects it onto the closest, let me write it better, closest point in C to X. You're talking about projection onto the convex compact set C. All right. So this is my first example of the proximal operator. If you take this indicator function, the proximal operator of the indicator function is actually the orthogonal projection. But more generally, you can do this for any weird object G. You can smooth it out by computing its proximal operator. And what is this precise definition? You minimize with respect to X, the sum of G of X plus a penalty X minus Z. But this is the proximal operator in Z. All right, I don't know that I want to spend much more time explaining all of the details, because this would be in itself a little mini course. But the point is that you can relatively easily define, it's well known that you can define something called the proximal gradient flow. So you compute the gradient of F, and then you do the prox of it. You do the prox of it. So specifically, imagine that I was doing this example with the convex compact set C. I could, and a specific example, this would be the projected gradient. In the projected gradient, I say minus X plus the projection onto C of X minus gamma nabla F. Gamma is a positive value, and sometimes you optimize it to get the fastest convergence rate. All right, let me conclude this discussion by saying that the proximal operator has very important properties, the most important of which is that whether you are minimizing the composite optimization problem or finding a fixed point of the proximal operator, it's the same point. It's the same point. And so when you write this proximal dynamics, when you look at the equilibrium of the proximal dynamics, you set that equal to 0, you're looking for fixed points of the proximal operator. So X gets mapped into itself. Now, there's a beautiful book by Beck. There's a beautiful survey by Parikh and Boyd that describe the property of the proximal operator. It's well defined. It's a generalized form of projection. It's non-expansive. It helps to generalize gradient algorithms to proximal algorithm, proximal dynamics. They're useful in many cases. In the book by Beck, I'm not going to go through this. There is a table. There's a table of functions. The notation I use is slightly different, so I apologize with respect to Beck. This is the function G, and this is its proximal operator. And so you can read the book and find. You may ask yourself the question, Francesco, how do I solve that little optimization problem to compute the proximal operator of a function? And the answer is certainly you can do it by hand. It's a very useful exercise. Either that, or you use your table of Laplace transforms. Or did I say Laplace transform? I meant to say proximal operators, because it's really the same story, right? Like you do in you define the Laplace transform, it has a certain integral definition, but then you use the table. And so that's the same is true for the proximal operator. So there's a table of a long range. And if I get around to the day after tomorrow, during the weekend, in your dreams, in your nightmares, I will be showing you other example of this proximal gradient. Now, why did I do all of this story? Because unsurprisingly, because this course is entitled Contraction Theory for Dynamical System, unsurprisingly, the proximal gradient is contracting, right? And there are estimates for the contraction rate. So it's contracting with respect to the standard Euclidean norm. Remember, the proximal gradient depends upon a parameter. So you obtain the range of parameters for which the dynamics is contracting, and the contraction rate will depend upon that parameter. And then what you do is you optimize the value of gamma, the parameter defining the proximal gradient, and you get your optimal rate. When people tell you this is the optimal rate, it's always a little bit of a lie, because this is an estimate of the rate. And so this is the value of the parameter that optimizes the estimate, not the rate itself. Does that make sense? So it's a bit the problem as before. In the conundrum is that if you do not have a proof that your rate estimate is the best possible one, it's the correct one, then when you say I have a bound, I'm optimizing the bound. Okay, it makes sense to do it. It's the best that you can do, but you run the simulation and maybe you discover that if you use gamma equal to twice that value, you get a contraction that is twice as or 4 times as fast. So then you do that, right? Just to be pretty clear. And there are other ranges for which the system is contracting, so that's also interesting. All right. The next and final example for this morning's lecture is going to be an example of a recurrent continuous time neural network. I'm just going to focus directly on this picture. This is an ordinary differential equation where, illustrated in this picture here, the picture is not important really. And I even have an output equation, which is not important right now, but that we will use later on, if depending upon time. This is the ODE that I am interested in. If you look at that ordinary differential equation, there are n nodes in the neural network, so this is n-dimensional. I use a very simple damping matrix, dissipation matrix here. It's just the identity, and it could be generalized, but this is very simple. And then I have X appears pre-multiplied by a matrix W. This is called the synaptic matrix. It's an interconnection matrix describing the strength of the synapses between nodes. To be honest with you, this model is not particularly biological. It's reasonably biologically plausible. You can find books in cognitive neuroscience which use this model. They call it firing rate or membrane potential. There's all sorts of words for it. There is a stimulus that appears, which is the control signal U. Sometimes people call this another constant vector here. They would call it the bias term. The point is that this fine function of the state is run through a non-linearity, capital Phi, which is called an activation function. So there is an activation function applied to a linear transformation of the state. And the activation function in general is non-linear. But I do want to say it is diagonal. What do I mean by that? I mean the following. Imagine that X has 2 components for simplicity, X1, X2. Then this function is really just a function of a lowercase phi of X1 and a lowercase phi of X2. That's what I mean by diagonal. Does that make sense? It doesn't need to be the case that the 2 entries are the same activation function. In fact, in the next slide, what I will say is that the activation function belongs to a class of activation function with certain properties. So every entry of the activation function can belong to that class and be arbitrary. Although oftentimes people use the same activation function for every entry. Now, allow me to just perform a very elaborate trick of mathematical machinery here. And that is the following. If I take the Jacobian of a diagonal activation function, and it's going to be a function of X1, X2, then what do I obtain? is, surprise, surprise, a diagonal matrix, right? So the Jacobian of a nonlinear function defined like this will have the derivative of phi evaluated at x1 in the first entry of the diagonal, and the derivative of phi evaluated at the second argument in the 2 entry. Does that make sense? So by their very nature, activation functions have the Jacobian that is diagonal. I'm going to use that property very soon. That's why I say it. These are the questions. So essentially the question is about this picture. In machine learning, people use feed-forward neural networks. They imagine having multiple layers, and it's not a dynamic, continuous time dynamical system. It's you give me an input, I multiply, and I get the output. Now, the model on the right is a generalization of the one on the left. The one on the left can be written as a special case of this one. You do not, this is not true that this is a single layer. I can certainly put topology inside the graph. Inside the W matrix, I can put multiple layers. This is a generalized version of it. It's called a recurrent neural network. But a feed-forward neural network is a special case of recurrent.
Does that mean the accidental?
No, because all I do, imagine I give you a W matrix. Take the main, you know what the main diagonal is. No, just shift it one layer up. Now, play with the synaptic matrix like this, and you will see that I can have, well, because what happens is going to be that x3 is going to multiply w2 and run through the activation function. And then that gets through multiplied that will appear in the first function. So even though here it appears that you apply the activation after w, the case on the left is a special case for a synaptic matrix with a particular topology. Yeah. Okay. As you well know by now, the name of the game is to show when is my firing rate model, recurrent neural network, strongly contracting. And with respect to which norm are we going to play the game? So we have played the game of the 2 norm. It is a painful game. There's much to be gained, but it certainly is not fun to play with the LMI. Let us try a different game. This is called the infinity norm. Recall, the infinity norm is, if I have a vector x, the infinity norm of x is the maximum value with respect to I of the absolute value of xi. Recall that if you have a matrix, the infinity induced matrix is the maximum row sums of the absolute values of A. So I could take A, write the absolute value, multiply by the vector of 1n's. So when you do that, you compute all of the rows, and I take the max of that. This formula is slightly different from the one I wrote yesterday. It's really the same, but in vector format. But when you take the log norm of A, actually, why did I use A? We have a synaptic matrix, which is W, right? So why don't we use W for a second? So it is W. And then the formula for the infinity log norm of W is the maximum. It's the row sums where you take the absolute values only off diagonal, right? We said that repeatedly. And so this would be the maximum with respect to I of each of the row sums, which is Wi, I, plus the summation under J from 1 through N, J different from I, of Wij, and I better not forget to put the absolute value around it. Does that make sense? So it's the formula that it's the log norm formula. It's in that table of induced norms that I had yesterday. Remember, in the 2 norm case, you get the singular value or the maximum eigenvalue, the symmetric part. in the one norm and infinity norm, you get row sums with or column sums with absolute values either everywhere or only of diagonal. Now, if I were to ask for mu infinity of W to be less than 1, suppose I were to ask for that condition, then the maximum is less than the maximum of a collection of numbers is less than 1 if and only if every number is less than 1. Does that make sense? All right, fine. So, but by the way, why are we considering the number? Why is the number 1 important? So imagine I take this particular problem. I drop the bias because it plays no role. And let's compute the Jacobian. The Jacobian of this dynamical system. That's actually a function of u as well here. Sorry, I forgot the u there. The Jacobian is going to be, I'm going to take the Jacobian of minus x, which is minus the identity, right? All right, fine. Plus. Now, for a second, allow me as activation function to take identity. So I'm not even going to do any calculation. I just imagine that phi of an argument is equal to the argument. So just keep it super simple. Then the Jacobian is going to be W, right? So if I want mu infinity of minus identity plus W, what is that equal to? So remember, the properties of the log norms are the properties of the real part of a complex number. So if you sum 1 to a complex number and you ask what is its real part, it's going to be 1 plus the real part of the complex number. So this is called the translation property of the log norm. So this is equal to minus 1 plus the log norm of W. And if you want this to be less than 0, you're going to get that you're asking for mu infinity of W to be less than plus 1. Okay. It turns out that even though I did this calculation for the case in which phi is equal to the identity function, it turns out that this is the right intuition, and you do need infinity log norm less than 1. Let me do, okay. You know what? Let's do things in order, because otherwise I get ahead of myself, and there's a reason why I defined various things in this slide. So let's be careful. Let's go slowly. First of all, we're interested in this neural network, which sometimes people refer to as firing rates model, where the nonlinearity phi is outside and the synaptic matrix W is inside. There are other models of neural networks where you have x dot equal to minus x plus W of phi of x, okay? Plus maybe an input or a bias, whatever else happens here, I don't care. But the point is that you may have the case where the linear operation is after the nonlinear operation. And some people call this Hopfield models. All right. Some people call those membrane potential models. The nomenclature is not widely accepted. Fine. Now, so I'm going to erase this orange thing here because we are sticking with just the non-linearity outside and the linear operation inside. So what activation functions are commonly adopted? Well, here are two in the pictures. One is the hyperbolic tangent, and the other one is ReLU, rectified linear unit. That's what the ReLU stands for. This is analytic infinitely differentiable, equal to its scalar expansion, and this one instead it's piecewise linear, and it has 1 point of loss of, it's continuous, but it loses differentiability at the origin. If you lose differentiability at a finite number of points, it doesn't matter at all. The whole contraction theory that I told you about works just through. Yesterday I made a quick comment. You use something called the essential supremum of the log norm of the Jacobian. You just don't worry about the points where you lose differentiability. That's the message. Compute the worst case log norm and you're fine. So you lose differentiability here you don't. Now it turns out that these functions, I'm going to just make this assumption that each of the entries of the activation function phi has derivatives wherever they are defined, almost everywhere, between 0 and 1. So between greater than equal to 0 means it's either constant or increasing. And less than equal than 1, it means that your derivative is never larger than 1. People call this non-expansive. I'll hopefully I'll finish soon. I want to at least make the statement. No problem. I'll make the statements and we'll do the proof later. Right. So the statement is that the firing rate model is infinitesimally contracting with respect to infinity norm, provided the synaptic matrix has this property that mu infinity of W is less than 1 with respect to the infinity norm. And I would like to also give you the rate. So what is the rate? The rate is, I'm gonna just introduce a little symbol, forgive me. It's this plus, it's actually the ReLU. So if you give me a number Z and I say Z plus, I mean to say Z if Z is positive, or 0 if Z is less than or equal to 0. Does that make sense? So here, when I write 1 minus infinity log norm of W, so if the log norm of W is positive and large, this is not gonna work. But when the log norm of W is less than 1, then what I'm saying is the best case scenario is then a contraction rate of 1. And the reason is that if you look at the equations, you always have a contraction rate of -1 from the first dissipation term. And then here you are allowing for an activation function that could potentially be constant. And if it is constant, it is not helping with the contraction rate. I think it's a good moment. We're all tired. It's a good point to stop. I will start the next lecture with finishing this little proof, which will be conceptually much simpler than the LMI one. And then we will move on to other example and theories. So thank you all. Have a great lunch, and I'll see you in a little bit.